What's up, y'all? This is your boy Mr. B here. Section 8.2.2, Properties of Logarithms. Let's go. Let's get it. So we've got this x to the fourth times x to the fifth. Just a little bit of review. You know that if you want to combine these two together, if you're multiplying the bases, then you're going to add the exponents. There's multiplication here outside of the exponent, and then that turns into addition. 4 plus 5 is 9. If you are dividing the bases, then you can say that 3 minus 1 is 2. Division becomes subtraction. And here, multiplication, exponents, you're raising t to the third to the fifth power, turns into multiplication. 3 times 5 is 15. Here, if you've got a radical, that turns into division. 15 divided by 3 is 5. Just as a summary, it kind of looks like this. If you see you're multiplying the bases on the outside of the exponent, then inside of the exponent becomes addition. Outside of the exponent, division becomes subtraction. And exponents, the power rule, b to the m to the n turns into b to the m times n, multiplication here. And radical roots turn into divisions or even reciprocals. So that's just a review here, and to get you used to the idea of inside the exponent and outside the exponent, like this here. This is outside. This multiplication is outside of the exponent, whereas this addition is inside the exponent. That's a property of exponents. We're going to turn everything on its head when we go to logarithms, and it's going to be kind of the reverse or opposite. Let me show you what I mean. We got log of 100 times 10, and I want to examine log of 100 times 10 separately from log of 100 plus log of 10. So anyway, if you multiply the inside of the logarithm, if you multiply 100 times 10, you get 1,000, and the log of 1,000 is 3, because you can take 1,000 and divide 10, the base 10 by itself 3 times to eventually get down to 1, or 10 to the third is 1,000. So the exponent is 3. Here, separately, you could do the log of 100, and that's 2, and a log of 10, and that's 1, and then 2 plus 1 is 3. So actually, the results are equal to each other, so therefore the originals have got to be equal to each other as well. Log of 100 times 10 is equal to the log of 100 plus the log of 10, which is really the result I want to look at. Let's do another example. We've got log base 2 of 8 times 4. Well, 8 times 4 is the same thing as 32. And how many times do you have to multiply 2 by itself to get to 32? It's 5 times. 5 is the exponent here that's missing. Separately, log base 2 of 8 is 3, because 2 times 2 times 2 is 8, and then 2 times itself twice is 4, so the exponents would be 3 and 2, and when you add them together, you get 3 plus 2 is 5. These two results are going to be equal to each other, so therefore the original expressions are also equal to each other. You notice there's multiplication here inside the log, and there's addition outside the log. Here we've got log base 3 of 9 times 9. That's 9 times 9 is just 81, and so 3 times itself 4 times is 81. 4 is the missing exponent. 3 log base 3 of 9 is 2, because the exponent you would have to put on 3 to get to 9 would have to be 2. And so 2 plus 2 is 4. So 4 is equal to 4. The results are equal to each other. What I'm trying to say is, if you take the log of something multiplication on the inside, that's going to be equal to log base x with the addition on the outside, log base y. That's the formula. That's the pattern. So the product property of logarithms looks like this. Log of any base a of m times n. And maybe you should put parentheses in here. There it is. That's a lot better. Log base a of m times n is equal to log base a of m plus log base a of n. In short, you could verbally say it, multiplication on the inside of a log turns into addition on the outside of the log, or vice versa, going forwards or backwards in either direction. So how this might look on alex.com would be, the instructions would say something like, fill in the missing values to make the equations true. Log base 9 of 8 plus log base 9 of 11. Well, you notice here the bases are the same, so we can use this property, and we can start on the right-hand side and go back to the left and say that log base 9 of 8 times 11 is 88. And so that's how you would just have to recognize that there's addition on the outside, so therefore that turns into multiplication on the inside. Or expand the logarithms to turn it into So here we go from 2 different logs to 1 log, and now we're going to start with 1 log and go to 2 logs. It's expanding it. Log base, and there's no way to calculate it. It would just be log base 10 of y, log base 10 of z. I wanted to show you over here. We got, if we wanted to calculate it, we go log base 9 of 8. Oops. Log base 9 of 8 plus log base 9 of 11. And the decimal equivalent is about 2, maybe 2.03772. And then we're going to do the same thing here. Let's see what the decimal equivalent of this is. Log base 9 of 88. And if you type them, you get the exact same decimal. So that's not. I do this calculations not to show you how to solve the Alex problem. Then don't pull out your calculator when you see this. But I do this to convince you of the fact that this is actually true. As weird as it looks, or as strange as it might be, or foreign as a concept, it's actually true, because the left side is equal to 2.03772 approximately, and so is the right. So therefore, they're going to be the same. Notice 9 squared. If the decimal equivalent were 9, were just exactly equal to 2, this number in here would be 81. It's a little bit higher than 81. And so then the exponent you would need is a little bit higher than 2. Okay, let's take a look. Let's use this property now to find out some more properties. If this happens to be true, then what else is going to be true? Like if there's, I wonder what would happen if there's exponents inside the log. Like this. You can see here log base 10 of 8 to the 4th. Well, if you want to figure out what exponents are, maybe we should just rely on multiplication, because exponents are just repeated multiplication. So if it's 8 to the 4th, that means you're multiplying 8 times itself 4 times. Log of 8 times 8 times 8 times 8. Now, using the property that we just discovered up here, we're going to actually expand them. Just like Alex says over here, expand the logarithms. Well, let's expand it. Log base 10 of 8 plus log base 10 of 8 it's written 4 times because there's 4 8s here being multiplied. So that's expanded. Now, if you wanted to contract it a little bit, you could just say that there are 4 of them. So, if this were x plus x plus x plus x, then that would turn into just 4x. So here, it's going to be the same thing as 4 times log base 8. And so that's kind of progress. So see, the 4 was on the inside as an exponent, and then it became outside multiplication. The same thing would be true if we just did it to the 5th. Log of 8 times itself 5 times would be a log of 8 plus itself 5 times, and therefore you could just put a 5 out in front and say there are 5 times log 8s. Here, log base 2 of 5 to the 3rd. Pause. I just wanted to do at least one of these where the base was not an unwritten 10, where the base was 2. It doesn't really affect the problem. Or the results. You still see the same pattern. 5 to the 3rd is just 5 times itself 3 times, and then there's multiplication on the inside, and we know from the previous property becomes addition on the outside. So if you've got the same thing like log base 2 of 5 plus log base 2 of 5 plus log base 2 of 5, there's 3 of them. You could just rewrite it as 3 times log base 2 of 5, 3 times. So the exponent on the inside becomes multiplication on the outside. Here, log base 10 of 6 squared, that's 6 times 6, that's log of 6 plus log of 6. There's, I'm seeing a pattern here. It's just every time it's going to be the exponent on the inside becomes multiplication on the outside. And so we don't have to do this one. Like, just take the 9 and write it out in the front and be done with it. It doesn't matter what the log base is. That does not affect the problem. So we can basically say the shorthand for this is the exponent on the inside becomes multiplication on the outside. And so if you have log base a of m to the p, that p, you can take that p and just move it out in front, p times log base a of m. So how might this look on alex.com? It might say something like, fill in the missing values to make the equations true. And you'd have to know that this exponent on the inside becomes a -3 on the outside. I actually just I paused the video for a moment for myself to insert parentheses, but I'm not 100% sure that even alex.com is going to give you the parentheses. It's worth talking about, is this 11? Is this log base a of 11? And then you take the entire thing, and the last thing you do is put raise it to the negative third power. No, the way this is written, and it might be a little bit tricky to think about, this is 11 to the negative third, and then take the log base a. Or put differently, is the negative 3 on the inside of the log, or is it on the outside of the log? There's no parentheses. And in this case, it's actually inside the log. You're taking the log base a of everything that you see here. We can talk more about that. I'll try and talk about it more in the video as well. Anyway, if it's inside, then inside exponent becomes outside multiplication. Here we got log base a of the fourth root of 7. Fourth root of 7 is the same thing as an exponent of 1/4. So that exponent of 1/4 becomes multiplication on the outside here. Here, log base 7 of 4. Well, I don't see any exponent. What are you supposed to do? And comparing it to over here, where'd this 2 come from? The bases are the same, but we're taking the log base 7 on both sides, but the power that's on the inside of the log is not the same. Well, you can actually think about it. You write 4. 4 is the same thing as 2 squared. So if this log base 7 is 2 squared, then the exponent on the inside is 2, becomes 2 multiplication by 2 on the outside. And here, the same thing in reverse. If you've got 4, there's no space, you could put as an answer 2 to the 4th, because 4 multiplying by 4 on the outside becomes an exponent of 4 on the inside. So 2 to the 4th, you could write 2 to the 4th here, but it would probably ask you to simplify. Log base 8 of 2 to the 4th would be actually 16. And if you wanted to expand the logarithms, then you're going to use the past two properties together in the same problem. I see multiplication on the inside, that turns into addition, and I see an exponent that turns into multiplication. So log base 10, that's be 6 times log base 10 of y plus log of z. Multiplication, exponent combined in the same problem. Quotient property. Well, I could prove this to you, but in the video. But I think the video is going to be long enough as it is. So if you really want me to convince you that this is true, then we can talk about it in class. When I see you next. But just suffice it to say that if there's multiplication on the inside, it turns into addition. Then if there's division on the inside, it turns into subtraction. So what it might look like on alex.com would be something like this. Here's a combined version. We've got exponents, multiplication, and division. And so log base z of all of this, if you wanted to expand this into sums and differences of logs, then you take the exponent here is on the x is 2, so that becomes multiplication on the outside. There's multiplication on the inside here becomes addition. Exponent on the inside becomes multiplication of 5. And then there's division here. So all of this is being divided by a z to the 4th, so it turns into subtraction. This exponent becomes 4, and then log base z of z. So this is log base z of x, log base z of y, and log base z of z. Now, log base z of z actually simplifies to something. You might remember if we do the log base 10, or no, I'll choose a different number. I don't know, some random number like 7. Log base 7 of 7, you get 1. That's because if the base is 7 and the power is 7, then the exponent you would need to go from 7 to 7 is 1. Or if you're using repeated division, 7 divided by 7 once is 1, and that's where you stop. In any case, even if you don't know, this is kind of a strange thing. We don't know what the base is. It's some number z, but it doesn't matter what it is, because log base 7 of 7 is 1, and log base 9 of 9 is also going to be 1. Log base 10 of 10 is going to be 1. Log base 100 of 100 is going to be 1. So log base any number of that same number is going to be 1. So even if you don't know what it is, doesn't matter what the value of z is, it's just going to evaluate to 1 anyway. So the answer you can write is all of this, and then this simplifies just to 1. So the last, it would just be like -4, and that's it. That's how it ends. Other thing that you type in. Let's try another one. Log base z, and we don't know what z is, but it doesn't matter too much. Log base z of all of this, the cube root of all of this, a squared b times c to the 5th. Well, the exponent, changing a radical to an exponent would be 1/3. So all of this raised to the 1/3 power turns into multiplication on the outside. You have 1/3 times, and then all of this business on the inside. 2 is the exponent. It's being multiplied. So the multiplication between the a squared and b turns into addition. Then you have the log base z of a, and then log base z of b would be here. You're dividing on the inside, so it turns into subtraction. And there's an exponent of 5, so it turns into multiplication. You're taking the log base z of a, log base z of b, and log base z of c. If this is confusing what I'm doing right now, we can also write up. I can show a bit more work and show a few more steps in class if we'd like tomorrow. But I didn't want to make the video too long. Let's do another one. So log base b of all of this. There's going to be 1, 2, 3, 4 terms because there's 4 variables. Log base b of a, there's no exponent. You're adding here plus 5 times log base. This 5 is a multiplication because there's an exponent of 5 on the inside of the log. You're taking the log b of this entire thing. All this is on the inside of the log base b. And both m and n are dividing a and y, so you'll have subtraction for both of these. The exponent on m is 2, and that's why there's 2 on the outside. Log base b of m, and I'll leave it to you to figure out what is here being multiplied on the outside of log base b of n. And before I talk about the last thing, I just wanted to drop randomly at this moment that my favorite convenience store is Wawa. I love Wawa. Grew up on Wawa. America runs on Wawa. I would say that also I love Wawa so much that I think that the Pennsylvania Department of Transportation, in order to get your driver's license, should have to include pulling into a Wawa space and pulling out of it as well, as busy as it is and as difficult as that can be sometimes. You've got to be able to navigate Wawa if you want to drive in Pennsylvania. Anyway, the last thing that I want to say here, you can copy down the green stuff. Inside the log, if you have multiplication that turns into, outside the log turns into addition. And if you have division on the inside of the log, it turns into subtraction. If you have exponents on the inside of the log, it turns into multiplication on the outside. And if you have a root or a radical, that turns into division or reciprocal. So take care. I want you to bring your questions to class tomorrow, and look forward to seeing you there. Take care.